This is a pretty long, complicated puzzle, but as always, I'm going to try to break it down and make it look easy with small steps. For this, you just need to know basic trig, a little bit of high school algebra, and there's a lot of logic here. Lately, I've been exploring all the logic and all the methods to figure out triangulation or locating the source of a signal by just using trigonometry, triangles, and whatnot. AI says there's a lot of different terms instead of triangulation, so you can look into those if you want to. But AI says a lot of things, and I've learned to take most of them with a grain of salt because they're often wrong. So here's a couple of different methods to locate the source of a sound, for example. If you set up some microphones, then the microphone that is the closest to the sound will register that sound first compared to the ones that are farther away. It's that simple. And we just use simple trig to get the direction of the sound. From what I can tell, it looks like there's a couple of different ways to use microphones to get the location of a sound. One way is where you put your microphones in closer together, where they're just a few centimeters apart. You have two microphones, say here and here. And let's say it takes sound 1 second to travel from one microphone to the next if the sound is traveling in line with those microphones. But if the sound wave, which is right here, comes up from a certain angle, it'll hit this microphone first. And instead of hitting the other microphone 1 second later, it'll hit the other microphone at some reduced time. So what I do is turn time into the length of that leg. For example, let's say sound travels 1 centimeter per second. It doesn't, I'm just using that for an easy analogy. So if sound travels 1 centimeter per second, and these two microphones are 1 centimeter away from each other, then it'll take sound 1 second to travel from this microphone to that microphone if the sound is traveling in line with the microphones. In other words, the sound is traveling parallel to the alignment of the microphones. But if that sound wave is traveling perpendicular to the microphones, then both of those microphones will register the sound at the same time, and thus you'll know the sound either came from the east or the west, or the right or the left, and then you put a third microphone somewhere to indicate from which one of those directions the sound came. So let's say the sound came from the bottom right, which would be the southeast if up is north. So here's the origin right here. You just take the time of the adjacent leg divided by the time of the hypotenuse. Take the arc cos of that and you'll get the angle. So then you'll know the direction of the source of the sound, but you won't have a location or a distance. So then you put a second microphone array, just like this one, somewhere else. It will also point to the direction of the origin of the sound. So wherever those two lines meet, then that will be the origin of the sound. In this case, it's good to remember that the source of the sound needs to be so far away that these two lines right here are measurably parallel. I say measurably parallel because theoretically they won't be parallel because they'll both point to one small location. But measurably parallel means that the difference is so small that we can't measure it. So for our purposes, we can consider them parallel. And here's another method to locate the origin of a sound. Method number 2 here. The other one was method number 1. So method number 2, we have a scattered array of microphones, and in this case, instead of being just a few centimeters apart, they could be hundreds or thousands of meters apart. And then if this is the case, you take the matching times on these microphones, draw a line between them, cut that line in half, and then, or bisect it, and then draw a perpendicular bisector. And so it'll look like this. Here's your circle, and here's two microphones at the same time. Here's two microphones at the same time. Their perpendicular bisectors will cross the center of that circle where the origin of the sound is. In this video, I'm not going to spend any more time on the second method. This video will be all about the first method. What I'm really looking at with this video that I'm doing right now, I'm not going to spend much time on actually how these microphones could tell you from which direction the sound is coming, because that's just simple trig, that's easy. I'm going to be focusing on the error rates and how to mitigate those error rates. And the errors will come from change in velocity of sound, because the velocity of sound will change with temperature and wind. Also, there is a way to do this with almost no math. You could just have a whole bunch of microphones arranged either in a wheel or a big ball. and whichever microphone gets hit first, then that's the direction from which the sound came. So here's the diagram right here. We have microphone A and B. Just for the diagram, I'll pretend that sound travels 1 centimeter per second. Therefore, if we have 8 centimeters between microphone A and B, that will be 8 seconds. That is if sound is traveling directly from the north or the south, or the top or the bottom of the page. In other words, if sound is traveling parallel with the alignment of the microphones. But here we have the sound wave coming in at this angle right here. The sound wave hits microphone B, and instead of hitting microphone A 8 seconds later, it hits microphone A 6.6 seconds later. And in this thought experiment, sound travels 1 centimeter per second. So if it takes 6.6 seconds to travel from this point here to the microphone, that equals 6.6 centimeters. Now we can just take the arc cos of 6.6 over 8, and we will get 34 degrees. That means the sound is coming from 34 degrees to the right and down. And technically we have a third microphone right here, and this will tell if the sound is coming from 34 degrees to the right or 34 degrees to the left. But in this case here, as you can see, the sound wave will hit the third microphone before hitting microphone A. Thus we know it's coming from the right or to the east. And what I say here, small array, this is where the microphones are just a few centimeters apart. Third mic, sound wave. Okay, so these microphones will only work if the source of the sound is so far away that these two lines are measurably parallel. Because, for example, if the origin of the sound comes from this point right here, this is 6.7 centimeters away, which means it'll be 6.7 seconds away from B. So as soon as something explodes right here where a gun goes off, then 6.7 seconds later, microphone B will hear it. And then microphone A, follow a straight path here. That's 11.4 seconds or 11.4 centimeters. Now there's no right angles in this new triangle I just drew. And so if this sound right here hits microphone B 6.7 seconds later, microphone B will register that sound at time 0, because microphone B has no way of knowing for how long that sound has been traveling before it hits the microphone. So we take 11.4 minus 6.7. This gives us 4.7 seconds later. This means that microphone B will be hit with the sound, and then 4.7 seconds later, microphone A will get hit with the sound. 4.7 is different than 6.6, so we'll get a completely different angle for our direction of the sound. And that new angle will be erroneous. And what I say here, so what we're doing, we measure the time, but then we turn that to the length of the leg of a triangle, and then we turn that into the angle to get the direction of the sound. And then I said right here, we will have a second microphone array in a different location, and that will point to the direction also. Then wherever those arrows cross, that'll be the source of the sound exploding there. And right here I made some notes. I said here, we want the time it takes for our sound to travel the adjacent leg after hitting the first microphone. So sound wave travels up, hits microphone B. We want the amount of time it takes for that sound wave to travel the adjacent leg of the triangle. And then we use that time to calculate a leg for that triangle, the distance of the leg, and then we use that to determine the angle. I said here the adjacent leg cannot be greater than the hypotenuse. So if sound is traveling directly up or directly north, it'll hit microphone B, and then 8 seconds later, it hits microphone A. That means the adjacent leg of this triangle has to be either 8 seconds or less. Here it's 6.6 seconds. If the adjacent leg was 8 seconds, then that would mean we're dealing with a vertical line. So if the velocity, what did I write there? If the velocity of sound decreases, the time will increase, or the time it takes for that sound wave to travel from one mic to the next will have an increased time. And then theoretically, we could end up with an adjacent leg that is greater than the hypotenuse. And then you just get a system error. So for this to happen, this would mean that say the sound wave is traveling against the wind, which will slow it down, and the temperature is going to be colder than what you had expected, and that'll make sound travel slower, and the sound wave is traveling roughly parallel with your microphone array. So for example, instead of taking 8 seconds to get from B to A, it could take 8.2 seconds or something. So just something to keep in mind. And here I said if you want to increase your accuracy, you could do calculations to account for temperature changes, because if the air is colder, then sound will travel slower. So for example, this sound wave right here will hit microphone B, but instead of taking 6.6 seconds to hit microphone A, it could take, say, 8 seconds or 7 seconds. Then it'll make it appear that this angle right here is narrower than what it actually is. I said wind is negligible because even on a really blustery day where the wind could be 30 miles per hour, the speed of sound is somewhere around 760 miles per hour. So you're only going to get somewhere like, I don't remember, 3 or 4% change due to wind, so it won't be a lot, even on a pretty windy day. What I'm going to show though is that using basic trig, you can actually negate or mitigate any error that happens from the velocity changes of sound, and I'll show how to do that. The reason I looked into this into such a huge amount of detail is because the first time I posted this video on just the basic trig, AI said this could never happen with just the basic math. They said this would never work due to sound velocity changes due to temperature and wind. So you're going to have to plug in equations to solve for that. But when I was playing around with these angles and these numbers, I was actually getting really accurate results down to just a few tens of meters without making any corrections for wind or temperature. So what I'm going to show in this video is how you can do these problems a certain way so that any changes in your angles due to temperature or wind, those changes will be negligible. Okay, so I think that's it for this page. Oh, also, AI said there was no way this would work with just simple math, because in my mind, I visualized it as having some microphones placed somewhere, and there could be a clock on these microphones that went down to, say, a millisecond time, and then after these microphones heard a sound. So for example, you could just leave the microphones on all the time to record ambient noise, and then whenever there was a report of a gunshot, you just take the recorder attached to these microphones, connect that recorder to a monitor, so you can see exactly when the sound wave started down to the millisecond, and then easily get the direction of the shooter. But YouTube AI initially said that there was no way that would happen without the proprietary software of the companies that sell the shot location devices, which are those microphones you put in different places to find the location of a shooter. AI said that the sound of a gunshot would be buried in ambient noise and echoes, so you'd have to have the software to filter out the noise. But I don't know how true that is because I've seen a lot of sound waves on monitors just over the years. And I even searched for images of sound waves that were being shown without any noise filters. And all the sound waves were pretty prominent, and they look like they'd be pretty easy to measure. And then as for echoes, sound waves travel out as if they're on a surface of a sphere. So if these microphones are in a direct line with the source of the sound, then the initial sound wave will hit the microphone first before any echoes, because if the sound has to reflect off of something, then that means it'll reflect off of something and then go to the microphone, which means it'll travel a longer path and it'll get there after the initial sound wave. And I'm just interested in the initial sound wave. So yeah, maybe if you have buildings all over the place, and so those sound waves have to bounce off of a lot of buildings before they get to the microphones, then that one would be tough to figure out. So maybe that's what the software's for. I don't know. At any rate, that's why I'm doing this video, and I'm showing the errors and how to correct for those errors. And that's because, like I said, when I was plugging in different numbers and different angles, I wasn't getting hardly any errors, and I wasn't making any corrections for temperature or wind either. So I'll show how I did that. Sound is a compression wave where all the air molecules are pushing into each other. So if all those air molecules are traveling with the wind, then that will speed up your sound wave. Any wind effect will be negligible. I just said here, for example, 30 miles per hour, pretty blustery day. That's about 13 meters per second. Speed of sound is 343 meters per second. 13 divided by 343 gives you a 4% increase or decrease in the velocity of that sound wave. And that's if the sound is directly traveling in line with the wind or directly against the wind. So 4% isn't much. I just showed here that temperature can cause a little bit more of a change with the velocity of sound as it travels, but it's not a huge amount. Here was the formula that was given on Google: 331.4 plus 0.6 times the temperature in Celsius. And this gives you the velocity of sound in meters per second. I used an M for Mach. So I'm using some fairly extreme temperatures here, -10 Fahrenheit, all the way up to 104 degrees Fahrenheit. I turn those numbers into Celsius, and I get the wind velocity in meters per second for very cold temperatures and very hot temperatures. Let's take the highest velocity of sound that came from very hot temperatures and subtract the lowest velocity of sound that came from very cold temperatures. We have 355 minus 318 equals 37 meters per second difference. Let's look at this as a percentage. So let's say the sensors on our microphones are set for very hot temperatures of 104 degrees Fahrenheit, but it's actually very cold at -10 Fahrenheit. We take 37 divided by 318, which is the velocity of sound in very cold temperatures. We get a 12% decrease in velocity. The reason that velocity decreases is because, we are in very cold temperatures, but we're expecting very hot temperatures, which would give us a very high speed of sound. Likewise, if our sensors are set for very cold temperatures, but it's actually very hot out, then we take 37 divided by 355. That's 355 meters per second, which is the fast velocity from hot temperatures. We get a 10% increase in velocity. So basically, we're looking at a 10 to 12% change in velocity in a pretty drastic situation. Granted, it's not Siberia, but -10 Fahrenheit is pretty chilly. So one way you can mitigate this is the speed of sound is typically given for a comfortable 68 degrees Fahrenheit or 20 degrees Celsius. I think that was 340 some meters per second. So that will lower your percentage error. And then, like I said, wind I'm not going to worry about. From what I read about humidity, it said the effect on wind velocity from humidity was negligible, and it has some pretty complicated formulas, so I'm not going to mess with that. Like I said, just using trig, you can actually negate any errors and actually get accuracy down to just a few tens of meters without making any corrections. And again, I'll show how to do that. So here's the logic. We have a microphone array here of A and B, heading, say, north and south. We have another array right here of B and C, oriented east and west. So for doing the math, we could either use microphones A and B or B and C. And I said right here, use the two microphones or the microphones in that array that are closest to 90 degrees from the origin of the sound. And this will greatly mitigate any errors that you will get from Mach changes or changes from the speed of sound. And I just said that here, changes in speed of sound. The triangle means delta, which means change. Here we have the origin of the sound, directly south, heading north, or directly at the bottom of the page, heading up to the top of the page. If that sound wave is either increased or decreased, you're going to see the largest effect when that sound is traveling in line with microphones A and B. So if that sound is greatly sped up or slowed down, then you're going to get a huge time change between A and B. So for example, even though that sound is coming from directly south, instead of taking 1 second to get from microphone B to microphone A, because for your calculations you're going to use 1 second, it could actually take 0.8 seconds if that sound is traveling faster. Then if you use 0.8 seconds, then that will give you a different leg on this triangle right here. And it'll look like the source of the sound is actually coming off to either the right or the left. So it'll look like the sound is coming from a different direction when you draw out your triangle with your right angle. But if you use microphones B and C for your calculations, the sound wave will hit both of those simultaneously, so you will have 0 time difference between those microphones. and thus you'll know the sound is either coming directly from the south or the north. So if the sound hits microphone A afterwards, you know that it's coming from the south, which would be directly due south. And I said here, line segment A and B will have a very large change in time. And that's because the sound wave is traveling parallel to that array of A and B. So if you have a large change in time, then you're going to have a large change in length, and that will give you a large change in angle. In other words, you'll have a large error. But if you use microphone array BC right here, then you'll have very little time change. So very little time change equals very little length change of that triangle leg, and that equals very little angle change, so which will give you very little error, or very small error. Thus, use the two microphones for the math that are closest to 90 degrees from the source of the sound. And that's how you easily mitigate any errors from the change in velocity of sound, which would come either from temperature or wind. Okay, next page. I'm going to show a really extreme example to show how well you can actually mitigate any errors. Let's take a 5-degree angle, so that wind is blowing almost directly from the south. Let's say it takes 1 unit of time, or 1 second, for that sound to travel from B to A if it's traveling directly in line with those microphones. North is up, the angle is 5 degrees. Here's the sound wave right here traveling up. It hits microphone B, but instead of hitting microphone A 1 second later, it hits microphone A 0.996 seconds later. Take the arc cos of that and you'll get 5 degrees. Thus, you know the sound is coming from the south, and in this case, it's coming from the southeast. But now, like I said, this is an extreme case. I'm going to increase the velocity of sound by 20%. So we're talking about hurricane force winds and extreme temperature changes compared to what we're expecting for our calculations. Basically, from what I read, this would never happen. You would never get a 20% change in the speed of sound, unless, like I said, it's in a tornado or hurricane or something. So what else did I say here? Okay, distance over time equals velocity, therefore distance over velocity equals time. So distance will be 1, just 1 unit, divided by velocity, that's 1.2 equals time, that equals 0.83. So if we have a 20% increase in the velocity of sound, then that means the sound wave will arrive at its destination in 83% of the time. And I just said right here, it's always a good idea to add your units to remind you of what it is that you're doing or what it is that you're calculating. So right here, for example, we have 0.9961 seconds for the adjacent leg, or you could say that's 0.9961 centimeters if sound traveled at 1 centimeter per second for our analogy. Okay, so let's take our time here, 0.9961 times 0.833 repeating for this factor right here. Basically 0.9961 pretty much equals 1, so we get the same number, 0.83 seconds. So the adjacent leg of our triangle goes from being 0.996 to 0.83. Take the arc cos of 0.83 over 1, adjacent over height, right here, we get 34 degrees. Therefore, we just turned our 5-degree angle into a 34-degree angle, which is an absolutely huge change and a huge error. We're going to be way off the location of that origin of the sound. Let's turn this into a distance to see how bad it is. Let's take our triangle, extend it all the way down, say 1,000 meters or 1 kilometer. That's over a half mile, so this is a pretty far distance. Let's take the sine of 5 degrees, which is our actual angle, and that'll equal opposite over 1,000 meters. We want this leg right here. That means the opposite leg is 87 meters, where it's 87 meters from this location right here. Now let's use the erroneous 34 degrees, which is our measured angle. Do the same calculations. Sine of 34 right here equals opposite over height, so opposite over 1,000 meters, and that gives us 560 meters for the length of this leg. Let's take 560, which is the measured, minus 87, which is the actual. That means we're off by 473 meters to the right or to the east. So basically just about 500 meters, and that's a pretty far distance. But I just said here, keep in mind, why are you doing these calculations? Is it for artillery or an address? If you're in town, you're going to be looking for a specific address or location where somebody might be shooting a gun. So in that case, you're going to want pretty accurate measurements. But if it's for artillery because you're going to shell a whole hillside because someone's up there sniping at you, then I would imagine that if you could get within just a couple of 100 meters, then that might be okay. But none of that's my field and none of this is my field. I'm just thinking out loud. Okay, so the reason we're so far off and we have such a huge error, first off, we have a 20% increase in the speed of sound, which may only happen if you're in a tornado in Death Valley or something. I don't know. And we use the two microphones right here that are in line with the sound or almost in line with the sound. So now I'm going to use two microphones that are closer to 90 degrees to the sound or 90 degrees to the source of the sound. And I'll show that on the next page. Now I'm going to use the same angle, south 5 degrees to the east or 175 degrees, which means it's, like I said, 5-degree angle here basically. But instead of using microphones A and B, I'm using B and C because that's close to a 90-degree angle from the origin of the sound. We have parallel lines here. Like I said, for this array to work, the microphones would just be a few centimeters or a few meters apart, and the source of the sound has to be so far away that these two lines are measurably parallel. Again, I say measurably, meaning that they won't actually be parallel, but they're so close to parallel that we can't measure any difference. Okay, so we have parallel lines, so that means if this angle is 5 degrees, this one has to be 5 degrees. 90 minus 5 equals 85, so this angle right here is 85. This one will be 90. That means this one has to be 5. You can see the videos I did on the proof for that if you want. So in this case, I said here the adjacent leg is the sound wave. The sound wave comes up right here, hits microphone C first. And the other calculations I did, it was the opposite leg that was the sound wave, but in this case, it's the adjacent leg. So you can see the leg of the triangle we're interested in here. I'm going to use the sine function, and this is a very small leg right here. And remember, the logic is if the sound is coming completely perpendicular to these two microphones, you will have a zero change regardless of how fast that sound wave is traveling. So since we're dealing with this particular angle of 5 degrees here and 85 degrees here, that 85 is almost 90. So this means we're going to have very little change or very little error from the change in speed of sound. Let's take the sine of 5 degrees. That equals opposite over 1. So opposite is 0.087 centimeters or 0.087 seconds, whatever you want to call it. And this is the actual measurement. Let's take the 20% increased velocity. This means that the sound will arrive at its destination in 83% of the time. So I wrote right here 83% of the time. Let's take 83% of the time times 0.087 seconds. We get 0.072. Take the arc sine of that to get our new calculated angle, and that'll be 4 degrees. So all we did was change our angle from 5 degrees to 4 degrees. And I said here a 20% increase in velocity caused a 20% decrease in the angle, because to go from 5 to 4, you subtract 20% of 5. But this only caused a 1 degree change in the angle, which isn't much. So in other words, that's very accurate, and I didn't make any adjustments for temperature or wind changes. So how this works, from what I can gather, and like I've said before, I just figured this stuff out and make a video. We have a very small leg on the triangle right here. So while we may have a large relative change, meaning we could actually take the length of that leg and either double it or cut it in half. So relatively speaking, we will change that leg a lot compared to what it was, but it'll be a small absolute change. So for example, if you go from 1 centimeter to 2 centimeters, that is a large relative change because you just doubled it, but it's a very small absolute change because we only gained 1 centimeter. So from what I can gather, that seems to be the logic on how this math works. So let's take our measured angle of 4 degrees. Sine of 4 degrees equals opposite over 1,000 meters. So let's carry this all the way out to 1,000 meters to the origin of the sound. Sine of 4 degrees equals opposite over 1,000. That means the opposite leg of our triangle equals 70 meters. And this was using the incorrect measured angle. Now let's use the correct actual angle of 5 degrees. Do the same sine calculation. We get 87 meters. So 87 minus 70 equals 17 meters off. In other words, we will be 17 meters to the left or the west. And that is because starting from right over here on the west, we only go 70 meters to the right instead of 87. So as you can see, 17 meters, which is approximately 17 yards, you could throw a rock and hit the person. So this was a very extreme case, like I said, extremely high wind, extremely hot temperatures, which would cause an extremely high increase in the velocity of sound. On the next page, I'm going to do a little bit more of a realistic example with only a 10% increase in the velocity of sound. This was what I was talking about when I said earlier, I was actually plugging in different angles and different numbers, and I was actually getting very accurate results without making any changes or any corrections for the changes in the speed of sound. And I'll show these calculations right here. Let's do a 45-degree angle. That way there is no set of microphones that is closer to 90 degrees than any other set. Because like I said before, you need to use the pair of microphones that's closest to 90 degrees from the source of sound. And at 45 degrees, you're right in the middle. So let's have a 10% increase in velocity from either wind or temperature. That's still a fairly extreme case, I think. Okay, here I said distance over velocity equals time. We are going to increase our velocity by 10%. So distance over velocity will be distance over 1.1. It's a 10% increase. This equals the time, which equals 0.91 of the normal time. This means the sound wave will get to its destination in 91% of the time. So we take the 0.71, which is the adjacent leg of our triangle, because it's a 45-degree angle, times 0.91, we get 0.65. So what this does, it changes the adjacent leg of the triangle from 0.71 to 0.65. We take the arc cos to get our new angle. Arc cos of 0.65 over 1 equals 49 degrees. So still what I think is a fairly extreme example of a 10% increase in velocity of wind. We just went from a 45-degree angle to a 49-degree angle, so not a huge change. And I just said right here, 45 is the actual, 49 is the measured angle. Let's see how far off we'll be then if we are going 1 kilometer out to the origin of the sound. And by the way, as you can maybe tell here, this is the sound wave going up, hits this microphone before it hits this microphone. And 1,000 meters away or 1 kilometer away is the origin. So we want the distance of the sine right here. So we're going to take the sine of this angle, which will equal opposite over hypotenuse, which is 1,000 meters. So sine of 45, which is the actual angle, equals opposite over 1,000. This equals 707 meters to the east to the right. And we do the same sine calculation for our erroneous measured angle of 49 degrees. That equals opposite over 1,000. Opposite right here over 1,000, which is the hypotenuse. This equals 755 meters to the east. Take our 755 minus 707. That gives us only 48 meters off to the right or to the east. 48 meters is a very close distance. I think a lot of people could throw a ball and hit somebody at 48 meters away. So it won't get you to the exact address, but it'll get you to the neighbor's house. And this is definitely close enough for artillery. And so this is depending on the purpose of your shot location device. So these are all just things I figured out. This was a long, complicated puzzle. There were, 100 steps here or something? I don't know. And that's what's fun about these math puzzles. So if you just do this stuff for fun like I do, and you're not being graded on it, then they are just very long, complicated, and very challenging puzzles. And every time you solve one of these puzzles, you learn a little bit more about the world in which we live and the universe in which we live. So everything looks good here. I'll go ahead and post this and I'll keep it up unless I find any errors. I almost forgot, I did do all these calculations for two-dimensional geometry. Most of the terrain on the planet is flat, meaning most of us don't live at the base of large mountains or skyscrapers where people will be shooting down on us. And most of the time we don't have airplanes overhead shooting down on us. So I figure the two-dimensional geometry should work. I think maybe you can imagine this as well. What if you're standing, say, on a hilltop somewhere or something, and there's a large explosion a half-mile away or so? And then say someone else is standing behind you in line with the sound wave, and that person behind you is, say, a half-mile away from you. That means the sound will take 2.5 seconds to get to that person. But if that sound wave is coming at some different angle, say for example perpendicular to both of you, then you'll both hear it at the same time. So it makes me think that an experiment like this could be done if the sound was loud enough and people were far enough away from each other. So say you hear a sound and push a button on a stopwatch, and then someone behind you was supposed to hear that sound, say 5 seconds later, if they were in line with that sound. But instead they hear it 2.5 seconds later, so they hit their stopwatch 2.5 seconds later. 2.5 is half of 5, so that means the sound was coming from a 60-degree angle. So it makes me think something like this would be theoretically possible, even with relatively slow human reaction times. If the sound was really loud, like a really loud explosion, and people were a really long distance away from each other. So that's basically all I'm doing here, except I'm just using microphones instead of people with stopwatches. So I'm thinking in that scenario, I don't think three-dimensional geometry would be needed if everybody's on relatively flat ground. I did a video that showed three-dimensional geometry for this, but I took it down to make some corrections and refinements. So maybe I'll redo that video and repost it.